Today, we're going to talk about one of the most elegant tricks in all of physics, the method of images. It's a story about how, sometimes, the only way to solve an absolutely impossible problem is to just change the rules of the game.
And you know the kind of problem I'm talking about. The kind that the more you stare at it, the messier it gets. No clear path forward. Well, in physics, that happens a lot. And it turns out the most brilliant solution isn't always to just grind through the math, but to find a clever way to sidestep the whole thing.
So to get this, we have to start with the rules. In the world of electrostatics, that's the physics of charges that are just sitting still, there's pretty much one master rule book that governs absolutely everything.
And this is it. It's called Poisson's equation. Now, don't let all the symbols freak you out. The core idea here is actually really powerful. It connects V, the electric potential, you can think of that like the voltage or even the height of an electrical hill, to ρ, which is just where all the electric charges are. So basically, you tell me where the charges are, and this equation should tell me the entire electrical landscape. It holds all the answers.
But here's the catch, and it's a big one. Just because you have the rulebook doesn't mean the game is easy. This is a partial differential equation, and trying to solve it for anything more complicated than a simple sphere is, well, it's a complete nightmare. So we have this ultimate law of the universe that's often too hard to actually use. To really see what I mean, let's look at a classic puzzle. I mean, on the surface, this thing looks so simple you could probably solve it in high school, but it's hiding a really nasty secret. Okay, so picture this. You've got a single positive charge, let's call it plus Q, just kind of floating in space. And right below it, there's a big flat sheet of metal. Now, because that plate is a conductor, our little positive charge pulls all the loose negative charges inside the metal right up to the surface. So the question is simple. How much force is pulling that charge down toward the plate? So, why is this hard? Seems easy enough. Well, it's because we have no idea how those negative charges actually arrange themselves on that metal plate. They don't form a nice, neat pattern. They create this messy, unpredictable smear of charge all over the surface. And trying to calculate the force from that hot mess, that's exactly the kind of brutally difficult problem our master equation just can't handle easily.
And this is where the genius comes in. Instead of trying to wrestle with that messy, real-world problem, physicists came up with an incredible workaround, a truly beautiful, elegant trick.
This is the big idea, the aha moment. What if you could invent a totally different problem, a much simpler one that just so happens to give you the exact same answer you need? You see, we're not going to solve the puzzle. We're going to replace it with an easier one. And here's the trick. On the left, that's our hard problem, with the real charge and the messy metal plate. On the right, we do something crazy. We just get rid of the plate. Poof, it's gone. And in its place, we put a fake, imaginary, image charge with the opposite sign, located at the exact same distance below where the plate used to be, like a perfect reflection in a mirror. This brilliant swap has a name, the method of images. You're literally trading a complicated physical object, the conductor, for a simple imaginary point charge. And the whole idea is that this fake charge perfectly mimics the effect of the real plate, but only in the space above it, which is the only place we care about anyway. I know what you're thinking. This feels like cheating, right? You can't just throw away part of the problem and make up something new, but it's not cheating at all. In fact, it's mathematically rock solid. Let's dig into why this perfect illusion actually works. The secret is something called boundary conditions. You can just think of these as the absolute, non-negotiable rules of the game for our specific problem. And for our metal plate, the most important rule of all is that the electric potential, the voltage, has to be zero everywhere on its surface. That's a physical fact we absolutely cannot break. And here is the magic. In our new fake setup with the two charges, if you look at that line right in the middle, exactly where the surface of the real plate used to be, something amazing happens. The positive potential from our real charge and the negative potential from our fake image charge, they perfectly cancel each other out. The total potential there is zero. Bingo! Our new, simple problem perfectly obeys the most important rule of the old, complicated one.
So why does that matter? Well, there's a super powerful rule in physics called the uniqueness theorem, and it basically says this. For any given electrostatics problem, there is only one possible solution. So if you find any solution that correctly follows all the rules, even if you found it with a crazy guess, then that is guaranteed to be the one and only correct answer. In our image charge setup, it follows all the rules. It's not a trick, it's the solution.
So, now that we've got our simplified, mathematically approved problem, what's the payoff? Well, this is the best part.
Now we get to see the real power of making a good guess.
Remember the original problem? The whole reason it was so hard was that messy, unknown smear of charge on the plate? But now, we just have two simple point charges in empty space. And calculating the force between 2 point charges is literally one of the first things you learn in Physics 101. It's incredibly easy.
And look at the result. It's just so clean and simple. The force pulling our real charge toward the metal plate is exactly the same as the attractive force between the real charge and its imaginary mirror image. We can write it down in this one simple, elegant formula. That calculation we thought was impossible, turns out it's trivial. Now just stop and think about that for a second. We didn't solve this because we had a bigger computer or were better at calculus. We solved it by being more creative. We completely reframed the question, took an imaginative leap, and turned a brutally hard problem into an easy one. You know, there's actually a wonderful German word for this kind of approach. It's Ansatz. An Ansatz is essentially a really smart, educated guess that you make right at the beginning, hoping it will simplify a complex problem. And the method of images, it might just be the most brilliant Ansatz in all of introductory physics. And this whole strategy, this idea of the Ansatz, is fundamental to how physicists work. It's a core part of their toolkit. When they face a monster of an equation, they don't just charge in. They make a clever guess. They test it against the rules, and if that guess works, it works. Game over. You've won.
And that leaves us with a really fascinating thought. We tend to think of physics as this rigid discipline of unyielding laws and cold, hard math. But as we just saw, sometimes the most powerful tool you can have for navigating those laws isn't a bigger calculator. It's a spark of pure, creative, human ingenuity. It's a beautiful paradox, right at the heart of how we figure out how the universe works.